Thank you. First of all, I would like to thank the organizers for inviting me here, and I'm already staying here for more than a month. It's a very nice place. Third time for me and him, and I enjoyed it a lot, as usual. So I would like to talk, okay, it's out immediately. And, so I would like to talk, but this thing does not switch in any direction. It's just, it doesn't work. It used to work. Okay. Yeah, it worked, but then it, thank you. That's what the organizers are for, probably for helping with this. So this is a joint work with Christoph Schwab, who's one of the main motivator for this particular work, and Vladimir Kazeev. And there was a good talk by Vladimir last week here about the theory. I will say a few words and my understanding of this stuff. And with two of my PhD students, Maxim Rakhuba, he is here, and Andrei Chertkov, he is not here. So what is QTT? Well, QTT is quantized tensor-train, and I will explain in details what it is. So FEM, you all know what is FEM, so no need to dissipate the acronyms. It's finite element method. So that's the problem, the model problem we are going to solve. So it's just the diffusion equation, probably with highly oscillatory coefficient and with scale separation. So we need scale separation for all of these methods to work. And probably if you have some random coefficient directly, these methods will not work. But for this particular case, we have, for one-dimensional cases, I will explain later, we have theory that it works very well. And both for one and two-dimensional case, we have solver that proves that this quantized tensor-train approach can be used for small delta, but also for all ranges of delta. So in fact, this is not sort of asymptotic expansion or something like that. It's just an automatic solver that gets a coefficient which can be oscillatory or can be very non-oscillatory, but it still computes the solution in this QTT FEM format. So we want to find the so-called tensor structure of the solution, and it's not so clear if so a tensor, it's just a, from my opinion, from my viewpoint, it's just a d-dimensional object, right? And this terminology is standard as multilinear algebra community, so probably people from algebraic geometry and probably from mechanics as well will not like this term for tensor, but it's just a short way of saying multi-dimensional array. And a fancier name. And well, you have d indices here, but if you have a one-dimensional PDE, well, there are no d indices, right? So it's not so clear how you use tensors in this case. Okay, so that's actually delta here. And I will explain the key idea how tensors appear here, and that I think the idea is very nice and very beautiful. I like it a lot because it seems to be rather non-standard, but still quite powerful. So if you have a this epsilon is actually delta, the multiscale parameter. So what we want to use, we want to take the multiscale problem, introduce a virtual finite element mesh that resolves the smallest scale. Well, in my example, I have two scales, but it can be 3, 4, or more scales. It actually doesn't matter much for the method. So the method does not explicitly use the amount of scales. So it only requires the diffusion coefficient. But still, in order to resolve the structure with low-order finite elements, like with linear finite elements, you need to take a grid size that is at least proportional, or say delta by 10, right? And of course, if epsilon is equal to 10 to minus 6, and you have a two-dimensional problem, you get a very small mesh, which you never can be able to compute in full. So you need to have a sort of compressed representation for that. And here comes the key idea of this QTT approximation. So what we do, we use a regular mesh. So in 1D, we just use a uniform mesh. Just a uniform mesh. In 2D, we use a tensor. So we restrict ourselves first to rectangle, to say zero Dirichlet boundary conditions, and uniform tensor product mesh. But still, if you have 1D case, so you take, for example, the standard low-order finite element basis. But what we require that the number of basis functions, the number of grid points is 2 to the power d. That's what we require. So we are not allowed to take like 511 points. We only need to have 512 degrees of freedom. Okay, it can be 3 to the power d, but 2 to the power d is the most convenient way. So we have this. Well, if it's not the case, you can always add some artificial grid points to pad it to the power d. That's actually not a big problem, but still. So then the next step, so if you are familiar with MATLAB or Python, there is a reshape function which takes any array and then you can reshape it into a 2 by 2 by 2 d-dimensional array using just a standard notation. So then you have a mapping from a vector to a tensor. So you can also think, so there are many ways of doing that, but the natural representation, so this i's, they are just binary digits of the integers. So you have an integer, you have binary digits, and that's the mapping. And then this is now a tensor. This is a d-dimensional tensor. And for this tensor, you construct a low-rank approximation. So we construct this tensor-train approximation, which I will explain in more details. And in fact, it appears in many interesting cases. If you have a function from a certain class, then this, instead of n parameters to represent this vector, you get something like log parameters where epsilon is the accuracy that you want to get. So you get, using this in fact purely algebraic scheme, because the construction of this tensor approximation is some sort of multi-dimensional SVD. So you can do it by using only linear algebra tools. You get the representation that has the number of parameters, that is logarithmic in both in n and in the accuracy. So that also means that you can quite easily store a vector of length 2 to the power 60 or 2 to the power 120, something like that, represent. Of course, you can do it the other way around. You can use not low-order finite element, but you can use a specially designed basis functions and or wavelet basis functions that represent your function in this basis, and then your function will be represented by the coefficients in this basis. But the advantage of this scheme is that you can represent absolutely different functions. For example, you can represent oscillatory functions and functions with pointwise singularities using this framework, and they both have this amount of parameters. Okay, I need to define what is this tensor-train approximation is. So that's the definition. So I'm not going to spend too much time on that, because that's not probably the main subject of this talk, and I'm a little bit tired of talking about this for more than 7 years, even or 8 years. But still, so for those who did not know what it is, so you have a tensor, and the whole idea is about the separation of variables. So you want to separate variables now, but the variables now are discrete. So the simplest is, of course, representing and d-index object as a product of objects that depend only on one index, right? But now the difference is that these guys are now matrices. So for a fixed ik, these are matrices. So graphical illustration could be you have this condition that if you fix all indices, you get a number. So you have a collection of rows here. You have a collection of small matrices here. So this is first mode, second mode, third mode. You have a collection of another matrices. And if you want to compute the elements in position, say 1, 2, 3, okay, in the end you have a collection of columns. You take this row, multiply by this matrix, multiply, for example, by this matrix, and multiply by this vector, and you get a number. So it's at each mode you have a collection of matrices and vectors. Yeah, so that's the format, and it has a lot of nice properties. So for example, given a tensor, you can compute these ranks, and you can compute a quasi-optimal approximation by running a sequence of singular value decomposition. So the code is actually very simple. So if you look in the details of the algorithm, well, 50 lines of MATLAB or Python code, no more. It's very simple. And it's actually some sort of generalization of the singular value decomposition from matrices to tensors. There are other ways of doing that. So H-Tucker is a more general representation, but this one is really simple. This one is really simple and often very effective. So all the programs, they are just some cycle from the first mode to another and running some reshapes of matrices, something like that. So there is something that I like a lot because that was first given in our paper with Evgen Terteshnikov. So you can recover a low-rank tensor from samples. So of course, okay, you can compute the approximation, but you are not allowed to compute all 2 to the power d elements of the tensor. But what we have, if you have the ranks bounded by r, it is enough to compute d times n in our case is equal to 2, r squared s, to exactly recover the full tensor. So that there is a very nice result which generalizes the matrix result that if you have a matrix, large matrix, but you know that the matrix has rank r, then you can recover it from r columns and r rows. This is skeleton decomposition. So-called skeleton decomposition. And there is a direct generalization of this thing from matrices to tensors. You can also compute approximate solution of linear systems, which I will talk about it later. And the QTT is what I already said, and we have a software that everyone can use. Well, documentation is not the best, but it works. And it has all of these algorithms implemented. Now let's go back to functions, right? So we're going to represent solutions of elliptic equations. So we need to know what are the functions that can be well represented in this format. So this is the first function. This too was in the paper by Boris Horowski. So if you have an exponential function with arbitrary lambda, right, and you do this scheme, then just using this representation, you immediately see that the exponent of a sum decomposes into the product of exponents. So you get rank 1. So exponent always has rank 1. And this structure is additive in the sense if you add rank 1 terms, in the end you get something that has bounded rank, and the rank is bounded by the number of summands. So everything that can be approximated by a sum of exponents has small rank. And this is already a large class, right? So for example, any rational function can be well approximated by a sum of exponents. And we do not need to know what are the precise lambdas, because we do not care. We only look at the final result. We know that the rank is bounded, and then we run, for example, the sampling algorithm. So the second example is more important to the multiscale, because any oscillatory function with uniform oscillation. So we need to adjust our grid to your oscillation. So if you have the function like this, right, that's a bad example. But if you have a uniform oscillation, it has rank 2. So if you have a uniform oscillation, it has bounded rank. Okay, you can write this, for example, in complex numbers by sum of 2 complex exponents, and each has rank 1. But that's actually, so this line actually proves that, or gives the hint why the multiscale with scale separation works well. You have point-wise singularities, which can be approximated by exponential functions, and you have uniform oscillations that can be well approximated also by low rank. So you have functions that have singularities, and you have functions that are highly oscillatory, but the oscillation is uniform. They are both have bounded rank, so any linear combination and product of those also has bounded rank. And for example, if you take the function like absolute value of x, it also has rank bounded by 2. So in fact, this is not related to smoothness, but this is related to point-wise singularities. And you can generalize this idea to 2 dimensions. So there the situation is more complicated. But still, so there is a wonderful paper by Kazeev and Schwab in 2015. Well, maybe Vladimir comes, so and I give a reference to his wonderful result. Well, maybe it's not so understandably written, but it's fully mathematically correct. And but if you put it down to a specific statement, so this representation, it has parameters, right? So you have to store, instead of storing a vector, you store this 3-dimensional object. So it's a non-linear parameterization of a function. And you need to store them. So that's the effective amount degrees of freedom. And the amount of degrees of freedom for the class of 2-dimensional elliptic PDEs and polygonal domains, okay, you have to think how you deal with polygonal domains and what is the forcing. But it's all in there, and it wasn't talked by Vladimir. So, but you basically have the amount of degrees of freedom behave logarithmically in the required accuracy. So it's epsilon minus alpha is wrong here, -1 should be here, and alpha should be there. So you have, well, more or less asymptotically optimal representation. Theoretically, and then that's a good idea to ask how you compute this representation. So you can probably use something like HP method to reach the same complexity, but in principle, this is much more easier to program when you have all the tools. So that's the idea of the proof that you said. So that's my interpretation of the proof. Of course, the proof is much fancier. But okay, you have if you have a 2-dimensional elliptic PDEs, you have corners, and the singularities can be only in the corners. So if you subtract the singularities r to the power beta, you get something analytic which you can represent, say, by Fourier series or something like that. And all of these terms have bounded rank. Okay, and then you write 40 pages of putting this down. And the PhD dissertation as well. But you know, that's actually, in my opinion, a breakthrough stuff, because before it was like, okay, exponent has nice rank, sine function has nice rank, okay, see the code works, but there was no single class. But a class of 2-dimensional elliptic PDEs with, well, analytic coefficient, I think it's quite interesting. So let's go to multiscale. So that was our paper that appeared last year. So 1-dimensional scale-separated diffusion equation, and that's really tough to prove. Actually, to prove all this. So the idea is nice, but proving this is this is another like 30 pages paper. But that's done. So at least in 1D for this problem, you have the dependence on the total number of degrees of freedom with respect to the accuracy, but now you don't only have the accuracy you want to get, you also have the multiscale parameter. The number of degrees of freedom is logarithmic both in the multiscale parameter and in the accuracy. So in principle, you can resolve very fine scales with the number of parameters that is logarithmic. And also what you can do, you can work in intermediate scales, like 10 to minus 2, 10 to minus 3, that are not so well approximated by the, for example, asymptotic expansion, but you can have very high accuracy there. Of course, there are many other ways how to solve that, but this is a confirmation that this approach works. So that's actually the statement. It's logarithmic in both in accuracy, well, in the energy norm, and in the parameter. So that's the final scheme, which is very simple. So, and that should be an algorithm, right? I'm not even yet into the topic of this talk about how you compute these things. But that's the final scheme. You have a function. You have a low-order finite element space. You approximate your function by an interpolant. You have the vector of coefficients, which has 2 to the power d elements. You reshape it into a tensor, and then you approximate this tensor by this low-rank tensor construction. Seems nice. But you need to find this, right? Because you do not have access to the vector, so you cannot work with the vector. So let's try to write the equations. So now instead of system of linear equations, you have some sort of nonlinear parameterization. So, and you need to represent the operator. That's actually something that is quite standard in our community, but still, so you have, in 1D you have a tridiagonal matrix, right? But this tridiagonal matrix can be huge. It's like 2 to the power 30 or 2 to the power 40. So 3n parameters is not something that we can afford. So we can use, but we can use approximation for the matrix as well. So if you have a linear operator that acts on a vector of length 2 to the power d, right? It actually can be considered as a linear operator that takes a tensor and creates another tensor. So it can be parameterized by an object that has 2 times d indices, right? So the matrix is also a tensor. And the right-hand side, well, if it's, for example, all ones, is also a tensor. And then we put this guy. So we can use, for example, Kronecker product approximation, but it's only for 2D. So we generalize it to ND. So actually, that's the tensor-train format for a matrix. So that's the tensor-train format for a vector, right? And this is the tensor-train format for the matrix. So it's important that this representation, since you have a product of matrices, and well, product of matrices is non-commutative, right? If you take 8, the order of indices is very important. So for one order of indices, you get one decomposition. For another order of indices, you get another decomposition. So here, the right order is that you couple together I1 and G1, I2 and G2, and if you are familiar with Kronecker product approximation, that's a very natural order. It's the most natural one. So that's what you get for a matrix. And this is something that is really easy to construct if you have, for example, a second-order finite difference approximation. So that's how you should do. So you want to put the matrix in the format. You put the right-hand side into this format. And so you basically have a linear system. So A in this format, F is in the format, and you want to find X that is here. And we have a very nice black box solver, so-called, well, the state of the art is so-called AMIN, alternating minimal energy solver by Dolgov and Sebastianov, and we have it implemented in both of the toolboxes. So the idea is, so since this is a symmetric positive definite operator, right? So you can, it's equivalent to minimization of the energy, right? And now we optimize the energy functional not over the whole space, but over the space of tensors of low rank. So now there comes a whole field of optimization with such low rank constraints. So Andrei Ushmaev is here working on that. So this is a convex problem, right? If you do not have this constraint, this is a non-convex problem. But still the number of parameters is now, so you optimize in the course, right, in the parameters. You can compute this functional efficiently. So then there's a whole field how you solve optimization problem. I'm not going to talk about that. Yeah, there are still a lot of open questions. So it's not clear how this method converge and theoretically and so on. In practice, they converge very well. And for example, one of the byproducts is that often you do not need any preconditioner. Why? Because you work on this low parametric representation, and this is already an a priori information where your solution lies. So it means you have like an a priori information. So suppose you know that you have a huge space and an ill-conditioned matrix, but you know that your solution lies on a linear subspace, right? Then you just solve your system with a Galerkin projection, basically. And now you have not a linear subspace, but a non-linear subspace. And you have, well, at each point, something like that. And these matrices are typically much better conditioned, not to say much smaller. So it seems to be nice, and that was our original plan, which, in fact, I think any student that looks into the paper can implement in a very short time. Well, not in a very, but not any, but a good student, not in a short time, but 1-2 months, but okay. So, but there was a funny problem that we encountered. Yeah, it was, so I'm not a finite element person at all, but that was really cool. So we want to use finite element method, low order finite element, for very small mesh sizes, really small, like 2 to minus 60. But they do not work. So they are unstable for very small mesh sizes. Oh, that, for example, what happens. So you have, well, so the green line is our new solver, which I will going to talk about. And that what happens if you like go here, and then the error of the finite difference solver goes up. So this is the comparison with analytic solution. So if you take something like, this is even not in multiscale, it's like something like that, which has an analytic solution and the finite, well, something like that. Probably this is not a good idea because then the accuracy is 0, but something like that. So you have an analytic solution, standard one, right? When you put known solution, get the right-hand side. And that's what happens when you go to very small h. And you can do it, for example. You can take a 3-diagonal matrix and actually to the power 20 tri-diagonal matrix is million by million, nothing. You can do it by yourself. And see that finite element method and double precision will lead to the growth of the error. And that's my explanation. I think it's a correct explanation. But it's only like an illustration of what's going on. I do not have a strict theory, but still. And this is a school thing. So that's Laplacian, right? That's what you have. And suppose you now work in finite precision, right? You have rounding errors. So if you work in double precision in 10 to minus 16, if you work in tensor approximation, you typically require something like 10 to minus 4, 10 to minus 5, something like that, right? And that's what you get from the error from the action of this operator. You have rounding error here plus h square, which is your scheme, right? That's standard. So actually, this cannot go to 0, right? So you have optimal h, which is a square root, fourth order root of epsilon, which is like 10 to minus 4, right? So beyond 10 to minus 4, finite element methods with double precision are useless, right? And that's why, by the way, you do not use finite element method with single precision, which is 8 digits formally, and you do not need 8 digits for finite element solution. You take often need 2 digits and 3 digits, but if you put 10 to minus 8 here, you will get that your finite element method will break for 10 to minus 2, right? So 100 by 100 grid, it will fail. Okay, but for 10 to power 4, even in 2 dimensions, of course, 10,000 by 10,000, this is not the grid you typically use. But still, if you want to go a very highly parallel computer and so on, you will not get accurate results with grids 10 to the power 4. That's kind of disgusting because this is a grid that you can get there. And okay, that's for general, but in our case, we need to have epsilon something like 10 to minus 6, and we need to go to very small h, and this just doesn't work. And well, that's a problem because this is a bounded operator, right? Delta minus 1, so it's a well-posed problem. So the error comes from rounding errors. So in exact arithmetic, everything is fine, but the rounding errors of the finite element, they are not included. And the discretization scheme in this is just not stable. Is not robust for h that is smaller than 10 to minus 4 due to rounding errors. And that's our solution. I do not claim it's the best solution, but it works. Just we found another discretization scheme, which has non-local stencil. And it is equivalent to the second order finite difference in finite precision arithmetic, in exact arithmetic. So it's equivalent in exact, but it's more stable. And let's illustrate this wonderful fact for 1D case, which is very trivial because this can be solved analytically, right? If this equation, it's very easy to solve analytically because you can just integrate it. That's kind of obvious. So we introduce a derivative as a new operator, and we have this equation. So that's actually the main idea. So since taking the derivative, numerical derivative is a bad idea, so let's just write the equation that u equals the Volterra integral operator of this derivative. And then instead of the boundary condition u at 1 equal to 0, we have that the integral of this derivative is equal, that's all. And then we discretize not the gradient operator, but we discretize this Volterra integral operator, which is actually in inverse of a discrete gradient operator. So that it is. Okay, and then we discretize that, and we get a very simple equation, but of course that can be easily solved. Have this, we have this additional constraint, and we have, of course, an analytic formula which comes from the exact solution. So this is the exact solution, which can be very easily computed for any small d. So you basically only have to invert the coefficient and multiply by this dense matrix B. It's now actually not a gradient, but a smoothing operator. We don't care because in this QTT format, this operator has ranks bounded by 2. So from the viewpoint of tensor approximation, the gradient and this guy are the same. They all have ranks 2. Yeah, and then you can, this is a stable formula. And you can show quite easily that this is equivalent to the second order finite difference with standard one when you sample the coefficients at midpoints and then you take the average there. And you can also bound the ranks of the solution. The ranks are bounded by the rank of the inverse of the coefficients times the rank of the sides. That's trivial. Okay, there are some numerics, but I'll probably skip quite all. Let's go to the two-dimensional case, which is much more complicated in the sense there is no simple formula. So, but now we have two derivatives, right? You have u of x, u of y. So we want to introduce derivatives as new variables. So we are not at the moment, I'm not at the moment caring about the function spaces and so on. So we do some formal derivation, get a numerical scheme, and then show that this numerical scheme in the exact arithmetic is equivalent to a certain finite difference scheme, right? So that's how we prove that this is scheme is okay. So, okay, differentiation is a bad operation. So we introduce two new variables. They are not independent because they are derivatives of the same function. So we have a sort of constraint like this, right? And we have, well, they are quite obvious. And one of that's how we do it in the paper. So we write down the energy. So these are our new variables. We want to minimize the energy. And after that, you have this operator, and then you have constraints. Then you have constraints, one constraint and two constraints for the boundary condition. So due to this operator integral from 0 to something, the boundary condition at 0 is automatically fulfilled, but you need to have some of this sort of equation to fulfill the boundary condition at another edge. So this is a constraint minimization problem. You introduce Lagrange multiplier for this constraint, and this constraint, and you optimize that. Okay, that's the grid. So you have to be careful, but you get a nice grid representation for that. And that's what you get in the end. So then we discretize the integrals. So we discretize the integrals, and then you have like the diagonal matrix here, the variables, the vectors that represent the derivatives, and you have constraints. And that's what you get in the end. You have a saddle point problem because this is a constraint minimization problem. You can exclude everything except for the Lagrange multiplier. You get for the constraint bx, ux, by, uy. So it comes from one Lagrange multiplier here. So I do not think it has any physical meaning. So by the dimension is some sort of second order derivatives, which may not even exist, but again, we do not care because this is all the discrete vectors. And you get some crazy thing instead of a nice second order differential operator. So for example, this one is a sort of inverse of the derivative. So this is the inverse of the coefficient. This is the correction that comes from the enforcing of the boundary condition, right? Well, that's the equation. And this is the equation we are solving. So we are now solving, using this Amin solver, we are solving this equation. So we are forming the inverse of the coefficient. We are forming this matrix QX, which is some sort of sum. So there is some machinery behind that, but it's possible to be done, and the code is not so short, and it's available online. So what we have shown that this crazy scheme in the exact arithmetic is equivalent to the second order finite difference scheme. So it's the same thing. So we have all the convergence result automatically from just the standard theory, where you do not take. But this is more robust, but I do not have any explanation why it is more robust. Because the condition number of this matrix is the same, we've checked it. But again, we only have like integral operators there, and in the approximate arithmetic is much more robust. We can work with accuracies like 10 to minus 6 and go to very small mesh sizes. Well, that's one numerical example. It's only a statement about the time, but we are able to solve on the grid with like billion times billion points, and the multiscale parameter 10 to minus 4 in around like 30 seconds on the laptop, which I think is quite cool. So there are some problems there with this part. So you have to, for example, carefully initialize the iteration method, but the solution can be computed. So it converts. So we do not yet have the theory for the two-dimensional multiscale. It's a work in progress, hopefully finished this year. But all the ingredients are there. But the solver is already working. Okay. Actually, I'm a little bit even faster than probably should, but maybe not so bad. So that's what I did not discuss in more detail. So, but okay, I discussed it here already. So that's how we compute the solution, low-rank solution. So we rewrite. So we have a linear system. We have a matrix in this representation. We have a right-hand side in this representation, and we formulate the energy functional, and then we minimize the energy functional. And the simplest method. Do I have the eraser at some point? Should be somewhere, right? Do not see. Okay, probably here. Maybe this one is better. Let's do it like this. So now I see that I discussed these questions on the way. So what you have this A applied to X, scalar product by X. This is a tensor, this is a tensor. The scalar product is summing all over the elements. Like this, right? And you have so the most straightforward method is to fix all of this X except one, right? So this is there is a multilinear structure, and now this is a linear thing, and you optimize only. So you do like block coordinate descent. So you optimize over one. So now in this particular core, it's quadratic, right? So you can write a small linear system for it and update. And in this way, this energy functional always decreases. And typically, you have quite fast convergence. So there are other questions, because for this method, you need to know in advance what are the sizes, what are the ranks, right? And there was quite a few works on how you adapt the ranks during the solution process. I do not think it's still done to full extent, but a good idea in this Amin method is to use some sort of gradient enrichment. So it's like some sort of approximation of the gradient. So do some step in the gradient and then project. So that's actually working in many cases very well. It's a black box. In the sense you just put the matrix there on the right-hand side, and then, okay, there are several parameters that you can tune for efficiency, but typically it works quite well. So the coefficient itself, K, is computed by the TT cross method, which samples the points and constructs the approximation. And so does, for example, the K minus 1, and all the stuff is also computed. So you have some black box optimization here, you have some machinery here, but it's really quite straightforward. So there are problems on the way, really, because you have this linear system for the mu, right? Oh, well, you can think of the energy, you can think of the result, doesn't matter much. And mu is something like the second order derivative of the true solution. So it's actually, if you look at mu itself, it's very bad, right? But you do not want to have mu, because you are not interested in that. You want to have small error here. So in fact, the schemes that adapt the rank, they try to approximate mu and they fail. So we had to modify them in such a way that they really minimize the error, which is equivalent to the L2 norm of the true solution. Okay, I do not have strict proof there, but it seems to be so. So what we are minimizing using the scheme, we're actually minimizing the L2 norm of the error. So probably this can be improved by better initialization or some sort of multigrid. So theoretical results for 2D non-oscillatory case, they are already there for 2 years already. So for the multiscale, it's not so easy because, well, you have problems. You have boundary layers there and so on, which you have to approximate as well. So it's not an easy story, but numerical results show that the structure works for the scale separated two-dimensional multiscale or 3D. So we do have the solver for 3D. It's more complicated. So it works for the non-oscillatory case. Yeah, but still, well, there are of course problems. So there's the references. Okay, let's do it. So this one is the theory, plus some numerical illustrations for the multiscale in 1D, that it works. This is our recent preprint about this solver, which is derivative free, and that's the same solver for the multiscale, which is in Proceedings of Ikamas. Yeah, so there's a MyScalTech group web page, and there are 2 toolboxes. So now I'm working more in Python, but the MATLAB one is probably in a better shape. So other people are maintaining it. And the code for this finite sum, right? So we call it finite sum because we do not take differences, we take sums instead of differences. It's also available online, so you can actually quite easily write the formula for the coefficient and, for example, analytic or something like that, and see how it will work. Okay, thank you for your attention. I'm done.